Okay, so the sensory receptors again are nociceptors, and nociceptors respond to tissue damage. They're also called the pain receptors. So if you're slightly touched on your skin, you're not activating a nociceptor. What would it take to activate a nociceptor? Some type of tissue damage. So if you're pinched really hard, that would damage some of the cells in the area, and so that would activate nociceptors. Real extreme heat would activate nociceptors. Chemoreceptors respond to chemicals, and we don't have chemoreceptors on our skin. We have chemoreceptors where? On our tongue, right? Taste buds. The reason we taste is because chemoreceptors are activated, and also in our nasal cavity. The reason we smell is because chemicals activate chemoreceptors in our nose, and those signals are sent on to the brain. So photoreceptors respond to light. Where do we have photoreceptors? In our eyes, right? So the retina is where we have photoreceptors. And what are the photoreceptors called? There are two types, rods and cones. So the rods and the cones are the photoreceptors. Don't forget that, it'll be on the test. So rods and cones are photoreceptors, and they're located where? The retina. And where's the retina? Huh? You have an idea? Looking at the eyeball, the picture of the eyeball. You have the front of the eye, the back of the eye.
It's in the back of the eye.
Right, so it's in the back of the eye, right. But we'll get to the picture of it. You all just had that test on it, so hopefully you remember. In the picture it was what color? Remember the color of it? In the picture. Y'all forgot that quick? Y'all just had it was yellow in the picture, I think. Okay, and then you have thermoreceptors. Thermo meaning temperature, right? So thermoreceptors respond to temperature. And then you have mechanoreceptors, and they respond to movement. Okay, so the type of receptor that is activated when you're just simply touched on your skin, or even if you have hair on your skin and you just touch the hair, that's activating mechanoreceptors. So the receptors are being moved, and that is what starts the signal. So the types of receptors. All right, and now we get to the special senses, the eye and vision. We'll come back. We'll get to that in a moment. Coast of the eye. So the sclera. So remember the coast of the eye. This is not the picture you all had on the test, but the parts are the same. So the coasts are also called tunics. You may see that word on the test. So those are the layers, so to speak, of the eyeball. So the outer layer, you have the choroid, and you have the sclera. Remember so the sclera is the white of the eye, and it is continuous with the cornea. And inside of that you have the choroid, which is referred to as the vascular layer. And then inside of that you have the what? The retina. So the retina is the inner coat of the eyeball. So if you just look at the eyeball as a sphere, the outer part of the sphere is the sclera. Inside of that layer you have the choroid, which is vascular, and that becomes important. And then you have the retina as the inner coat, the inner layer. Okay. Do you all have what I'm looking at?
No, that's all good.
Okay. Okay. Yeah, this is the one. So, and the last one we didn't have proprioceptors, so the rest of them are the same. You have proprioceptors that detect position of body parts, again, and then the chemoreceptors and photoreceptors. And so tactile corpuscles found mostly in the dermis of the skin around hair follicles. And so you all may remember that from the integumentary system. And then there are pressure receptors in subcutaneous tissue. What is the subcutaneous tissue? What does that even mean? What does cutaneous mean? Skin, good. So skin, beneath the skin, that's what it means. So it's beneath which layer? So we have how many layers of skin? Really 2, right? What's the outer layer? The epidermis, and then the dermis, and then hypodermis, which is the subcutaneous. Okay, so the deeper, the reason they're called pressure receptors is you have to kind of touch deeply in order to activate those receptors. And pain receptors are free nerve endings, and so these are found on the skin, muscles, and joints, and also in some of the internal organs. The brain has what? No pain receptors. So why do we have headaches? Because of other tissues around there, right? Blood vessels, meninges, muscles on the skull. All right, so the sense of temperature receptors are referred to as thermoreceptors, and we have separate thermoreceptors for heat and cold. So if you stick your hand in a container of ice water with ice in it, that's going to activate the cold thermoreceptors, whereas if you're sticking your hand in hot water, it would activate the heat thermoreceptors. And then those signals just go to a similar part of the brain but slightly separate, so the brain is able to interpret the difference based on the types of receptors activated. Okay. Temperature receptors, thermoreceptors, also in the hypothalamus. So that's the hypothalamus, remember, is what regulates our body temperature. So they detect when the temperature is fluctuating, either too high or too low, and makes the proper adjustments. And again, the sense of position, proprioceptors, are located on muscles, tendons, and joints, mainly at the areas of our joints. And they relate impulses of body parts in relation to each other. So that's how we know the location of our body parts without looking at them. And also impulses are sent to the cerebellum to help maintain coordination. 5 special senses: olfaction, and you all should know that word by now. Olfaction, olfactory. So that's the sense of what? Smell. Gustation, taste, good. And then you have vision, equilibrium, and hearing. Equilibrium has to do with balance. Okay? So if our equilibrium is off, we may feel what? Dizzy, right? Dizzy. The room may feel like it's spinning. Yeah. You heard of vertigo? That's an issue that has to do with the equilibrium being off, and it's debilitating. We've all been dizzy at some point, and it's not really a good feeling. But just imagine all day, every day, you have that sensation. So that would be unbearable, I think. Okay, olfactory organs. So these organs provide our sense of smell, and they're located in the nasal cavity on either side of the nasal septum, and they're made up of 2 layers. So we're talking about the organs that detect smell. So these again have chemoreceptors. So the 2 layers are olfactory epithelium and the lamina propria. And the olfactory epithelium is the part that includes the receptors for smell, or a sense of smell. So these receptors are activated by chemicals. Also in this area are supporting cells and stem cells, which give rise to new cells. And this is kind of a picture showing you those cells that are involved. So you can see here on the bottom of the picture the blue cells here. And so these are the olfactory cells and their cilia. And the cilia contain receptors, and you can see those chemical particles are moving up toward those receptors, and once they bind to the receptor, that starts off the signal, the action potential, which carries the signal on to the brain. Okay? And then the other cells, you have supporting cells, and that's what they do, support the olfactory cilia so that they can do their job properly. Okay. One of the things, I think one of your study hints asks, what is required in order for us to be able to smell something?
Is there another requirement for molecules? Another requirement for molecules to be smelled?
Right. So the requirement for us to smell molecules, what is that? Anyone look that up? So basically all it is that the particles, in order to be smelled, have to be in vapor form. Can't be solid, right? Because the particles have to actually make it to your nose. So if you're smelling something, the chemicals have to actually bind to your receptors for you to smell it. And that just grosses me out. When you smell something that smells bad, walk by, dog poop, and you smell it, when you think, okay, those particles have to bind to my receptors in my nose for me to even smell it. I just don't like that even being in my nose. All right, so the olfactory receptors have to detect the dissolved chemicals. So the chemicals have to be dissolved and in the gaseous state. Olfactory discrimination, so we can distinguish thousands of chemical stimuli, and the CNS interprets smells by the pattern of receptor activity. So what we'll see also with the taste buds, we'll get into, in fact, that's coming up now. So with taste, you also have chemoreceptors that have to be activated. And so the chemoreceptors are taste receptors, also called gustatory receptors. And it provides information about the foods and liquids that are consumed. So the taste receptors are distributed on all portions of the tongue, pharynx, and larynx. And they are clustered into taste buds. So the taste buds are what make the surface of the tongue rough, called lingual papilla. Actually, it's the lingual papilla, which some contain taste buds and others do not. So the types of papilla, lingual papilla, filiform, fungiform, and circumvallate. And the filiform do not contain taste buds. So those are the surface papilla, just providing the rough surface on the tongue. And but the fungiform contain 5 taste buds, and the circumvallate papilla contain 100 taste buds each. So the circumvallate are the most active of the taste buds, or the papilla, I guess I should say. All right, so they also contain basal cells, gustatory receptors with hair cells, and they only survive 10 days, so we are constantly renewing our taste cells, our taste receptors. And here's a up close look at the taste port. So whatever we are tasting has to be, so there's a requirement for us to taste substances as well. So in order for us to taste the chemical, it has to be dissolved in water or the saliva. So if you have a completely dry tongue, you won't be able to taste. And the liquid makes it into the taste pore where the receptors are activated. And then you can see where the signal travels on through axons to the brain. So the taste sensations, the primary sensations that you all need to be aware of are sweet, salty, sour, and bitter. So those are the 4 primary taste sensations. And you'll find that there are different receptors, types of receptors for each, and they're located on different parts of the tongue. You may notice a stronger sense if you put something on the tip of your tongue that's sweet versus salty, and that just lets you know that there's a difference in the concentration of a particular type of receptor on different parts of the tongue. 2 other taste sensations, umami and water. Water has a distinct taste. So it is one of the taste sensations added to the 4 primary sensations. The umami is characteristic of beef, chicken broth, and Parmesan cheese. I guess what happens is they can't fit those into any of these. So Parmesan cheese, you all try Parmesan cheese? Where can you fit it into any one of these? It's not sweet. Somewhere between salty. I would put it between salty and maybe a little bitter, maybe. But and chicken and beef broths. Now beef kind of has a distinct taste, right? Beef is not really salty, not really. So those have their own type of sensation, taste sensation. Gustatory discrimination. This one's interesting. So when you think about it, in order for us to be aware of different tastes, for example, you taste something sweet versus salty. How do you know? So the signal has to make it from your taste buds to your brain. So what do you think is different physiologically between the ability to interpret something as sweet versus salty? What do you think the reason for the difference is? The different types of receptors, right? So when you have something sweet on your tongue, you're activating one type of receptor, just the sweet receptors, but you're not activating the what? Salty receptors. So the sweet receptors are sending signals to a particular part of the brain, and salty receptors are taking it to the same area but just a slightly different part. So that's how we have discrimination between tastes. But what about, you can tell the difference between something being very salty versus slightly salty, right? Something could be so salty you don't even want to eat it anymore. So what is going on different, you think, in your brain at that point? What's the difference? Physiologically, you think? What may be different? Yeah, so how is it that your brain can tell the difference between something very salty and something just slightly salty? So we're activating salty receptors with both instances. Good. Very good. So if something is very salty, you're activating more of those salty receptors. So we have some salty receptors that just respond to slightly salty, and other salty receptors that respond only when it's extremely salty or sweet. So the neurotransmitters generate the action potentials. Also, the signal may travel a little bit, the action potentials may come a little bit faster if it's extremely salty. Okay. Now to the eye muscles. We talked a little bit about these when going over the cranial nerves. So the cranial nerves involved in movement of the eyeball are 3, 4, and 6. So what is cranial nerve 3? 3 is oculomotor. Good. What is 4? Trochlear. Yeah. And 6 is abducens. Good. Okay. So now you can see the eyeball has all these muscles around it. And these are skeletal muscles we control when they move left and right, up and down. But notice where the muscles are and the names of the muscles. So we have superior, inferior, lateral, and medial rectus muscles. So we have 4 muscles, 4 rectus muscles around each eyeball. Superior rectus would be above the eyeball. So when it contracts, what does the eye do? Moves up. Okay, so the superior rectus muscle, when it contracts, the eyeball moves upward. The inferior rectus muscle is beneath the eyeball. When it contracts, the eyeball moves down. What about the lateral rectus? So the lateral rectus muscle will move the left eyeball to the left and the right eyeball to the right. And then the medial rectus will move the eyeballs toward the nose, toward the center. Good. Okay? So again, the oculomotor nerve is going to innervate most of those. The trochlear innervates the superior oblique. So we have 2 obliques, inferior and superior oblique. And you can see the shape of them. So if you think about the shape of the muscle fibers, that tells which direction the contraction is pulling the eyeball. So with this one being going around the eyeball in that way, you can see that it's probably going to rotate the eye. So the oblique muscles, when they contract, the eyeball slightly rotates. Not a whole lot, just slightly. And so you can see the obliques will move the eyeballs in around in a circular motion. Okay, so the obliques, and then the cranial nerve 6, remember, is the abducens. So it stimulates which of those muscles? You remember? The lateral rectus, good. Because it does what to the eyeball? Abducts the eyeball. So that's going to mean that it stimulates the lateral rectus muscle. Okay, so those are on the test. Make sure you all go back over that. The innervation of the extrinsic eye muscles, so we just mentioned those, and the nerves involved. And the nerves supply to the eye. So of the cranial nerves, looks like 5 of them have something to do with the eye. So the optic nerve, we know what it does, right? So you all should have an idea what each of these nerves, actually know the functions of each of them, all 12 of them. But so the optic nerve has what to do with the eye? Provides vision. Okay? So if you cut the optic nerve, what happens? No vision. Blindness in that eye. The oculomotor nerve. Eye movement. So the oculomotor nerve innervates some of those extrinsic eye muscles. And notice that word. Let me go back to that for a moment, because you'll see extrinsic muscles and intrinsic muscles. So keep in mind, extrinsic probably means what? Outside. So these are the muscles outside of the eyeball. We'll see in a few minutes that there are intrinsic muscles. So when you see that on the test, you'll know extrinsic is referring to these 6 muscles that move the eyeball. So the oculomotor nerve and the trochlear and abducens, we said those 3 move the eyeball. And what about trigeminal? facial sensation, and that includes sensation of the eyeball. Good. The accessory structures of the eye, the eyelid, the conjunctiva, and lacrimal apparatus. So the conjunctiva, so that's kind of the pinkish area of the eye. There's a part of it that is under the eyelid and part of it that is on the surface of the eyeball as well. And then the lacrimal apparatus is the apparatus that has to do with tear production of tears. And so that's going to be the glands. The lacrimal glands produce the tears, and then the tears move through. Let's look at a picture of it. So a lot of people think the lacrimal glands are here, right, in the corner of the eyeball, the center, or actually on the corner on the side of the nose, the medial part of the eye, because that's where tears tend to pool, right? The tears are made superior and lateral to the eyeball, and the tears flow through the ducts, the lacrimal ducts, onto the surface of the eyeball, but then they pool in the center, close to the nose. So you have a little hole that you can see there, a pore, which is called the lacrimal punctum, and that's where the tears will enter the lacrimal sac and empty into the nasal cavity. And that is one of the questions study hints is, why do we cry? Why do we blow our nose when we cry? And that's because the tears, again, end up emptying into the nasal cavity. So tears flow across the eyeball, helping to wash away foreign particles, delivering oxygen and nutrients, and also preventing infection.
Well, you said the tears form the nasal before it's what?
Yes, so the tears are made by the lacrimal glands and empty through the lacrimal ducts onto the surface of the eye, and then they leave the surface of the eyeball through the lacrimal punctum into the lacrimal sac, where they're emptied into the nasal cavity. Okay. And so, of course, if there's too much of the tears, then some will flow over the lower eyelid. But that's how the mechanism is. So the eyeball again has those 3 layers. So we're getting to the eyeball again. Here's our picture. So the retina, we asked about the retina. It is here. Okay. Try to get the color right up here. So the tunics. So what are the 3 tunics of the eyeball? The outermost is the sclera, inside of the sclera, choroid, and inside of the choroid, the retina. So you can see the 3 layers there. And so on the test, I'll ask you kind of the function of each of those layers, each coat. You can almost imagine the outer coat is probably serving what function? Protection. Okay? So the sclera is kind of hard, not as easy to penetrate. So that's a tough fibrous layer. The choroid is referred to as the vascular layer. So anytime you hear that word vascular, you should be thinking blood vessels, right? So that's where the eye's blood vessels are located. So that's the nutrient source for the rest of the eye. Okay, so remember, all cells have to have some blood supply in order to get the what? Thank you. Everybody? Why do all cells need blood flowing to them? Thank you. Okay. When you all leave here, at least know that. If you don't know anything else, know that the blood is carrying oxygen and glucose to all the tissues. For what purpose? All right. All right. Y'all with me. Okay. So the inside of the choroid, you have the retina, and the retina is made up of what? What's the significance of the retina? It has the rods and cones, which are the what? Photoreceptors, right? The light receptors. Okay, so in order for us to see, vision is a sensation, you have to activate a receptor. So the receptor is activated in order for us to see our photoreceptors, and they are in that retinal layer. So it makes sense then that we want blood vessels close to those photoreceptors. Okay, and then there's something called detached retina. Y'all heard of that before? So a person has detached retina. Just looking at the picture, what do you think is detaching from what? So you would think the retina is detaching from the choroid, and that's exactly what happens. So this space here is filled with kind of a gel-like material, and when it's full, it pushes the retina against the choroid. But if for some reason that starts to sag, or it diminishes, the retina can pull away from the choroid, and that obviously can lead to blindness, because now the cells of the retina are no longer getting their nutrients. Okay, so protection, vascular layer, blood vessels supplying nutrients to the rest of the eye, and the retina has the photoreceptors, the rods and cones. And notice on the retina, there's an area that is called the fovea centralis. The whole area is the macula, but in the center of the macula, you have the fovea centralis, and that's an important part of the eyeball. When you look directly at something, notice if you look directly at something, that's in the dead smack center of your eyeball. So whatever you're looking directly at is falling on your fovea centralis. And in that area, you have a very high concentration of cones. So cones provide light vision, about light and color vision. And the rest of the retina has a mixture of rods and cones. So rods don't give us as clear a picture as cones do. So because there is such a much higher concentration of cones in this area, that's why it gives us our highest visual clarity, which I call high visual acuity. And I'll do a quick demonstration to you all. If you hold on a second. Okay, so look at me. Everyone look at me. All right. So I'm going to flip this paper over. When I flip it, don't look at it. Okay? Don't cheat until I tell you to look at it. But while you're looking at me, you can see the blemishes that are on my face. Don't look at that yet. And while you're looking at me, you can't see what's on this paper, can you? You can read what's on the paper while you're looking at me? You cannot. You cheated. If you can read it, well, maybe because you're at a distance back. But most of you, while you're looking at my face, you can see everything, all the blemishes on my face, but you can't see what's on this paper, right? And that is because when you're looking at me, I'm falling right here, but this paper, while you're looking at me, is falling somewhere else on the retina. So you still see it, but it's not clear. It's not as clear as when you're looking at me. So even if you can see it, it's still fuzzy, right? It's a little fuzzy if you're not looking directly at it. And that's the point I wanted to make. So all of the retina is receiving signals, but the photoreceptors are clustered, the rods and the cones. But the fovea centralis has what again? A very high concentration of cone cells, which provide the highest visual clarity. Okay, so even when you're looking straight ahead, you can see the ceiling, you can see the floor, right? So just think about it. So if you're looking straight ahead, the reason you can see the ceiling, well, the light from the ceiling is falling on what part of your retina probably? So this person, if they're looking straight ahead, they can see the ceiling, but where is the light from the ceiling falling? Probably on the lower part of their retina. Okay? So whatever's on this side of me, I can see the door, but the door is falling on the medial part of my left eyeball and the lateral part of my right eyeball. Y'all get that? So when an image makes it to your retina, it's going to be inverted because of the direction or the path of the light making it to the retina. Okay? And a couple more parts that I'll ask you on the test to know. So the functions of those, the blind spot, forget about that. The optic disc is referred to as the blind spot. Any idea why? Right, so you can see in the center part there are no photoreceptors. Okay? So no photoreceptors are present in the optic disc. That's where the axons are carrying the signal from the photoreceptors onto the brain. Okay, so they're not going to be receptors in that area. The optic nerve, you know what it does? The optic nerve is made up of what? Axons. Axons that are connected to neurons associated with the photoreceptors. So those signals have to make it to our brain. What part of our brain? In order for us to see? What part of the brain? Yeah, occipital lobe, right. Okay, so the signals are being transmitted in that direction. And let's see what else. The ciliary bodies. So notice you have ciliary body here, and there are ciliary muscles. So there are smooth muscles in that area. And the ciliary body is connected to these ligaments, suspensory ligaments. And the suspensory ligaments are connected to the lens. So the lens is here. And when light comes into the eyeball, it passes through the pupil, which is the space, and then passes through the lens. So the lens has the job of focusing. So that's the area of focus. The lens has to focus. It's trying to focus the image properly on the retina, on the right part of the retina. Okay, so that's the job of the lens. So the job of the ciliary body is to manipulate the ligaments so that it properly adjusts the lens. So those kind of work together. The ciliary body has the muscles which manipulate the suspensory ligaments which change the shape of the lens. And we'll see in a moment how the lens changes shape based on the distance something is to us that we're looking at. And so the iris is referred to as the color part of the eye. But what's the function of the iris? It's not to provide color. It's the color part of the eye, but that's not the function of it. Any idea of the function of the iris from the autonomic nervous system? There you go. It controls the diameter of the pupil. Okay, so it constricts to let less light into the eye and dilates to allow more light into the eye. And we've mentioned that before. Why do we want to be able to regulate how much light comes in? What happens if there's too much light? The pupils constrict, but why? Why not stay dilated?
You don't need light.
What can too much light do? Damage what? Yes, the retina. It can damage the retina. So if it's a bright sunny day, the pupils, you don't want them to dilate. And you all have had your eyes checked when they dilate your pupils. Yeah, so you have to wear those protective glasses to prevent too much light from entering, and it can damage the retina. And we talked about light and dark. When you first turn the lights off at night, what happens? You can't see that well. Why? Right, so before you turn the lights off, your pupils are slightly constricted, right? Not as much as it would be if you were out in the sun. But if your lights are on, you have a partial constriction of your pupil. And when you turn the lights off, that's not enough light coming in to the eye, so you don't see. But after a while, a few seconds, you'll start to be able to make out the objects in your room because the pupils start to what? Dilate. So you should have an idea what causes the pupils to constrict and dilate. If it's light versus darkness, you know that light causes them to constrict, darkness causes them to dilate. And what about sympathetic and parasympathetic activity? Sympathetic causes them to dilate, and parasympathetic constrict. Good. Okay, and the cornea is just the clear part of the eye. It's continuous with the sclera, but it's clear, whereas the rest of the sclera is opaque. The pupil, the lens, I think that's all I have on the test that you all need to know about. Okay, so you also have fluid. You have vitreous. It's called vitreous humor versus aqueous humor. Vitreous is kind of a thick liquid, more like a gel, and that's going to be in the area behind the lens. Anterior to the lens, you have the anterior humor, which is a more watery type of liquid. Okay. All right, so how do the pupils dilate and constrict? Smooth muscles, and the smooth muscles are referred to as pupillary constrictors and dilators. And a sphincter, heard of a sphincter before? What is a sphincter?
It allows, I know that you have one in your mouth, so like all you hold and open your mouth without stretching too far.
Right, so they're really circular muscles, right? And so we have sphincters in the other parts of the body as well, but if it's a sphincter, that means that if that muscle contracts, then it's going to close whatever the opening is, or narrow it at least. So the pupillary sphincters constrict the pupil, allowing less light to enter the eye. And notice on the picture, I wanted you all to kind of get an idea of how that works. You have the iris, but how are the muscles contracting and constricting and dilating the pupil? So the circular muscles, you can almost imagine if a circular muscle contracts, what happens when a muscle contracts? It just gets shorter. So if the muscle contracts, obviously that's going to make the opening smaller. But the pupillary dilators have a different orientation. They're kind of oriented going away from the center, more linear than circular. So when these muscles contract, you can see that they're probably going to what? Pull the sphincters open. Okay? So the pupillary dilators, these muscles are the ones that are innervated by the sympathetic division. Okay? Y'all see that? So the parasympathetic division would stimulate which of the muscles? The pupillary constrictor muscles. Okay? So that's an interesting point there. So that's kind of how this picture on the left is how your eye would look after you've had your pupils dilated. The rods and cones. So the retina contains the rods and cones, and these are the photoreceptors that must be activated in order for us to see. So when are the rods functioning? In dim light. Very good. And rods do not allow us to be able to interpret colors, just shades of gray. So notice when the lights are off, even if I turn the lights off in here, there's some light coming in, but it will be harder to determine colors. Have you noticed that? Sometimes if you can see in your room, in your closet, but if you don't turn the lights on, you can't really make out colors that well. That's because your cones are not active when the lights are off. Okay, you need light in order to activate cones. So the rods are functioning when the lights are off. So you're able to see only shades of gray. Okay, and the cones are active when the sun is shining or when lights are on, and they allow us to see color. So they provide color vision. And again, the cones are densely clustered in the fovea centralis. And this is just a good look at the structure of the retina. When you look at it in the previous picture, you can't see that all this is going on. But this is light going into the eye. Let me see if I can show you another picture. Yeah. So you can see that, so the light is coming in this direction. But notice that the light has to come all the way through to the back of the retina to activate this pigmented layer, which is where the rods and cones are. And then the signal moves forward. And I'll show you the types of cells. And most of this I won't put on the test, but it's just good information for you. So when light passes through the eye, it first hits the pigmented part of the retina, and that activates the rods and cones. So notice the cells at the top there, that the top of the cells have a different shape. That's where the name rods and cones come from. So the cone cells kind of have the tip at the top, and the rod cells are more rod-shaped on that end. And so once they're activated, they send the signal forward to the bipolar cells, and then forward to the ganglion cells. And the axons of the ganglion cells are what become the optic nerve. So the optic nerve is made of the axons from those ganglion cells. It's very interesting. Okay. And there's the fovea again. Let's look at, I mentioned the aqueous humor, and so that's the liquid in the anterior and posterior chambers. And intraocular pressure, you'll hear about that with glaucoma. People who have glaucoma have an increase in intraocular pressure, and that is fluid pressure in the aqueous humor. And it's important because it retains the shape of the eye, but it can damage the retina if it is the pressure is too high. And I did want to mention cataracts. So cataract is a condition in which the lens has lost its transparency. So notice where the lens is. Whatever light comes into the eye passes through the lens. So you want the lens to be clear so you can have a clear picture. But the lens, if a person has cataract, and we all will if we live long enough, it's just something that's going to happen. At a certain age, it's just more prevalent. But it becomes cloudy. The lens becomes cloudy. So if you've ever worn glasses and your glasses get foggy, how difficult it is to see is kind of like that. But it's easily treated. It's easily treated. So cataracts is where the lens loses its transparency, it becomes cloudy. Light refraction, that's just the bending of light whenever it hits an object. And for you all, the main thing here is accommodation. So remember, what is the purpose of the lens? Focus, right? So it has to adjust its shape in order to properly focus the image onto the retina. And astigmatism occurs where light passes through the cornea, but the light is not bending properly because the shape of the eyeball or the shape of the cornea is a little distorted. Okay, let me show you that here. So normally, if you're looking at an object close to your face, you have notice the lens, how the lens is different. So in the picture on the top, the person is looking at an object close to their face. The picture on the bottom, they're looking at an object far away from them. But look how the lens changes depending on whether you're looking at something close to you or far away. That is called accommodation. How the lens changes shape. When you're looking at something close, the lens tends to become more round, and it flattens out if you're looking at something far away from you. So for close vision, the ciliary muscles contract to make the lens more rounded. And for distant vision, when you're looking at something far away from your face, the ciliary muscles relax, and that causes the lens to flatten out slightly. And as I said before, when you're looking directly at an object, you can see what's above and below it. And whatever is below it is going to fall on the upper part of your retina. And whatever is above what you're focusing on will fall on the lower part of your retina, so that the image arrives inverted onto your retina. And nearsighted, so here's a couple of terms that you'll see on the test. Myopia and hyperopia. Myopia is nearsightedness, another word for nearsightedness. And so what does that mean, though? So if a person is myopic or nearsighted, that means what? Right, so they see things better up close to them. They have a difficult time reading things at a distance. So that's nearsighted. And the problem is due to the eyeball being longer, a little bit longer than normal. So when we're looking at directly at something, where do we want the image to fall on our retina? What part of our retina? The fovea centralis. So when you're looking directly at something, notice the perfect image is going to land on the fovea centralis. Well, all right. So in this individual, the perfect image falls in front of the fovea, in front of the retina. Okay? So the image that actually hits the retina is going to be fuzzy. And that's because the eyeball is too long. So with corrective lenses, what that does is make sure the proper image falls right there in the center of the fovea centralis. So that's with myopia. Hyperopia is just the opposite. So if a person is farsighted, that means what? They see things better if they're a little bit further away from their face. And the reason for that is because their eyeballs are shorter than normal. Okay, so nearsighted people have long eyeballs, farsighted people have short eyeballs. And that's different for people who become farsighted in their older age. So as we get older, the lens will change on us, so we all become slightly farsighted as we get older. But if a person is born farsighted, it's because their eyeball is a little bit short. So corrective lenses make sure the object falls right there in the center of the fovea centralis. And so problems with accommodation, remember that's how the lens changes shape. Surgical correction is possible. You all have heard of LASIK. Anybody had LASIK surgery? Mm-hmm. LASIK. That's where, so some people don't want to wear contacts and glasses anymore, so they'll have this. Okay. So yeah, so that's pretty common nowadays. So color blindness, one of the things I didn't mention is we have rods and cones, but there are 3 types of cones. We have red cones, green cones, and blue cones. So if a person is born, for example, without red cones, then they'll be colorblind. Or if they're born without any of the color cones. So color blindness is the inability to detect certain colors because you lack those cones, those particular types of cones. So if a person was born without red cones, they wouldn't see a number there. Everybody in here see the number? Okay, so that's an early test done to determine whether a person is colorblind or not. Depth perception. Another question in your study hints. What are the requirements of depth perception? Anybody find that? So in order to have depth perception, what is depth perception? Good. So our ability to judge how close something is to us is our depth perception. So just looking at me now, you know you can reach out and you won't be able to touch me, right? So if you didn't have depth perception, you may think that you were able to reach out your hand and touch me from where I am. So what is necessary in order for us to have depth perception? 2 eyes. That's why we have 2 eyes. That helps us to determine how close or far away something is to us. And you can practice it. You can just cover one eye, but since you already know in your current position, you would have to kind of close your eyes, walk around, and then cover an eye, and you may think you can touch somebody, that they're close enough to you to touch them, and they're not. Okay. And the ear. So the parts of the ear, you all had a picture similar to this. So just know the main parts of the ear, the auditory ossicles, the eardrum. So you have the external acoustic meatus, auditory canal, and so sound waves travel into our ear, and when they hit the eardrum vibrates, and that vibrates the auditory ossicles and the oval window, and then that triggers activity within the cochlea. So remember, the cochlea is where we have our receptors for hearing. So the main thing here for the test, and there's quite a bit, actually this chapter is very long. It's chock full of information that we just don't have time to go over. It would take me quite a bit of time to go over everything. But when you all get a chance, read the whole chapter. Okay, you might not do it during the semester, but when you get some off time, it's good for you to have a more of a strong foundation in how the body works. And the ear is amazing. The whole body is amazing to me. But so the cochlea is where we have our it's called the organ of hearing because that's where our auditory receptors are located. And the vestibular apparatus, the vestibule semicircular canals, have the equilibrium receptors to help us to maintain balance. The vestibular nerve, cochlear nerve, the name tells you what they do, transmit the hearing signals and equilibrium signals from the inner ear to the brain. The auditory tube, also called eustachian tube, you all may have heard it referred to as the eustachian tube. This is an interesting part. A lot of times babies get ear infections, because the auditory or eustachian tube is not in an angle like that. It's more linear. So when they drink milk and they're sleeping sideways, the milk gets in their ear and that can set up infections. So that's why they have a lot of ear infections. But the purpose of the auditory tube is to maintain pressure, equalized pressure on both sides of the eardrum. You can imagine if there's too much pressure on this side of the eardrum, it's going to kind of push it that way. If there's too much pressure on this side, it's going to push it that way. Neither one of those is good, so the eustachian tube is there to kind of balance it. So when we yawn, chew, any of those things help to normalize the pressure on the inside and outside of the eardrum. So that's the main thing there. So know the names of the 3 auditory ossicles, and those are bones, right? So the ossicles are bones, you should know that. And then you have muscles in there as well. And so you have the tensor tympani and stapedius muscles. And those are important because if you hear a very loud sound, like a gunshot very close to your ear or really loud music, it can cause the eardrum to vibrate too much, and that can cause damage to the inner ear. So what these muscles do is tense up to decrease the effect on the inner ear. So it prevents the damage to the ear. Okay, so reduces movement of the stapes at the oval window. This is the stapedius muscle. Okay, and then the semicircular canals. Let me show you the receptors there. I think I have them. So these, depending on how you move your body and your head, these areas of the inner ear will react in such a way to activate the receptors, and that's how the equilibrium works. So when you move your head, I think I have a good picture of it here. So when this guy, you can see his head is upright, but when he moves his head backward, that moves the gel that's in the inner ear, and that activates the receptors. So the movement of the head will trigger activation of the equilibrium part of the brain, equilibrium part of the inner ear, which sends a signal on to the brain. So that is it. That's all I wanted to go over for today.